Welcome to Finite Element Analysis lectures by Civil Thinking, and today we are going to start our lecture series on finite element method or finite element analysis. So before I move on, I suggest you to please watch the video lectures on finite element analysis one by one as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now, first of all, let us first talk about these two: finite element method. Okay, now it's also called as finite element analysis. Okay, so they are one and the same thing, although this finite element method, this terminology is used in universities. Okay, and this finite element analysis, this terminology is used where? In industries. Okay, so they are one and the same thing. So the first two words of finite element analysis or finite element method are what? It is finite element, right? So the question is, what is finite element, right? This is the question. So what is finite element? So what is finite element? Finite element is something, with fixed dimensions. Finite element, for example, you have this square, for example, this is 2 mm, okay, and this is 2 mm, for example, 2 mm. Now this figure have fixed or finite, right? Finite dimensions. Okay, so this is a like a fixed measurable quantity, right? So this is a finite element. Okay, we call this as finite element. Not only this, when it have uh, only a few or finite degrees of freedom. Okay, for example, it can move left, right, it can go up or down. Okay, or it can rotate. So if we have measurable degrees of freedom, okay, so when we have a finite degrees of freedom and we have finite dimensions, so that thing is a finite element. Okay, so this is a finite element, right? So this is the concept of a finite element. Okay, so let's move further. Now the question is, what is finite element analysis? Okay, now finite element analysis, because the first two words, finite element. Okay, so what we do in finite element analysis, for example, we have any body. For example, this is a cantilever. Okay, cantilever beam, and we want to analyze it. For example, we want to find any property. What property? Anything like stress, strain, deformation, anything. Okay, any engineering property, right? So if it, for example, it would deflect like this when we apply a load, right? So maybe we want to find how much did this deflect. Okay, how much did this deflect at this point, and all of these, and how did we get this deflection curve? Okay, how did we get this deflection curve? Okay, so in order to find these engineering properties, okay, we use finite element analysis. Okay, but what is the concept of finite element here? Basically, what we do, whenever we analyze an engineering problem, we divide the domain or the body into finite number of elements. Okay, for example, like this. Okay, what we did, we divided this beam into 1, this is 1, okay, 1, all of this is 2, all of this is 3, and this is 4. Okay, so we divided the whole continuous body, continuous object, into discrete, into finite elements. Okay, so this is one finite element, this is another finite element. Okay, so this is another finite element, and this is another finite element. Although this beam, it is continuous, right? This is continuous. Okay, but what we did, we converted it. Okay, we converted it into, okay, we converted it into, you know, a few number, okay, a definite number of what, finite elements. Okay, so this is, okay, this is discretization. Okay, discretization, this process is called discretization, in which a continuous body is converted into discrete element. Okay, then what we do, because we have converted this, for example, beam into you know, discrete elements. Okay, then what we do, we find the, for example, we want to find the deflection. Okay, we find deflection here, maybe we get this point, and deflection of this point is up to here. The deflection of let me erase this first. This point is, for example, up to here. The displacement of this point is up to here, and this point did not displacement. Okay, so we found what, we found the engineering property that we want. We found them on fixed number of pointers. We call them as nodes. What? Nodes. Okay, so nodes are, what are these? These are, you know, points. Okay, we found the deformation at only fixed nodes. Then the question is, okay, I know the deflection here, I know the deflection here, deformation here. What about this point? This point does not lie, there is no node here, right? Because in finite element analysis we always find, what, first thing is we find at what, we find the property at nodes. Okay, then in order to find, you know, let me get rid of this. Then in order to find the deformation in between, the property in between, we, what we do, we interpolate. Okay, so if we want to find here, so we will interpolate it. Okay, so we'll get this too. Okay, so in this way we interpolate between two nodes and we get the engineering property between two. Okay, so this is this, you know, in simple terms, this is finite element method. Okay, so if I write about this, so finite element method, okay, is the method in which we find an engineering problem, okay, or we find the engineering property by what, by dividing the continuous body into discrete number of elements. Okay, then we find the required property at the nodes of those discrete elements, and then in order to find the deflection, not deflection, anything, in order to find the property, required property in between the nodes, we interpolate. Okay, interpolate. Okay, so this is basically finite element method. Okay, so I hope you got some, you know, the basic idea in simple terms. Okay, so let us move on. Now we have different methods of solving an engineering problem. Okay, now first of all, what is an engineering problem? Now engineering problems, you know, like finding stresses, strains, okay, temperature variation, or things like velocity in fluid, whatever. Okay, they are all what? Engineering properties. Okay, for example, we found the deflection, okay, of the cantilever before. That was also an engineering problem. Okay, now there are basically three methods, okay, to solve. Okay, we have three methods, and they are this. Okay, analytic method, and then we have experimental method, and then we have numerical method. Okay, so let's talk about analytical method first. Now what we do in analytical method, basically, this analytic method, as we know, the equations, with the help of equations, so we have governing equations. Okay, for example, in case of a cantilever, for example, you have a beam. Okay, let me take a simply supported beam. Okay, okay, for example, a load is acting here, then it will deflect somehow like this, right? Then what we have some governing equation. For example, in case of beam, d square x by d square y by dx square, right, is equal to m divided by ei. Okay, then moment is, for example, p times x divided by ai. Okay, so we have this equation, right? We have equation, right? A governing equation. Okay, so when we find the deflection, for example, we find the deflection here, or we draw the curve, we use what? We use an equation. Okay, so we use governing equations. Okay, and they are almost 100% accurate. Okay, they are accurate. Okay, what is the problem? Why do we need numerical methods or experimental methods? The problem is equations are not always available. Okay, and they are also good for simple problems. When we design a product in engineering, on when we face real life, they are complex problems. Okay, and we don't have always equations like this. Okay, these equations are derived based on like assumptions, the bending theorem and all those things. But in real case, in the reality, these equations are not available. Okay, so we cannot rely on analytical method always. Okay, then we have the second method is experimental method. Okay, now what we do in experimental method, as understood, we do the experiments in lab. What we do, we need prototypes. Okay, with the help of prototypes we do the testing. Okay, then maybe we use, for example, strain gauges here. The strain gauge will tell us what is the deformation here and all those things. Okay, so basically what we do, we need prototypes. Okay, we need prototypes and we do the actual tests on them. Okay, they are also 100% accurate almost. Why? Because we practically do the experiment in the lab. Okay, then there is numerical method. Okay, and the finite element method lies here. Okay, FEM is a numerical method. Okay, what happens here, instead of using these equations, we don't. Okay, we use this is a differential equation, right? This is a differential equation. So we use we assume things, we assume something, and we get simple, like what we call them, algebraic equations. Okay, algebraic equations. So what we do, we convert the differential equations what we do, we convert them into what? Into these algebraic equations. Okay, algebraic equations. By how do we convert? We make some assumptions. Okay, we make some assumptions. Okay, because the algebraic equations, these are very easy, much a computer can handle it very easily, okay, but these differential equations are quite hard to handle by a computer, because the finite element method, because the most of the engineering softwares like ANSYS, like Abacus, right, or some other like SolidWorks, they are all based on finite element method, okay, the numerical method, okay. So we need algebraic equations or algebraic matrices, because matrix is a type, a form of algebraic equations, right? So when we make assumptions, okay, remember, when we make assumptions, what happens? When we make assumptions, this leads to errors, okay, because we made them assumptions and they may not be true, okay. And this is why the result here are what? Approximate, okay. So although the results are approximate, but the good news is that we can apply the numerical methods in real world complex problems, okay. So this is the thing, we need finite element method, okay. Although we don't get actual result, we get an approximate result, right? So this is why we use numerical method, okay. So I think that's it for this topic, and let us move on. Okay, now here is a question of why FEM, okay, why finite element method, okay. So let me write finite element method or finite element analysis is a numerical method, right, to solve complex engineering problems, okay. The results are approximate, and as as we use the finite element method, if we increase the number of elements, okay, or nodes, okay, because elements are made of nodes, and if we increase them, then the accuracy of the result will increase, okay. So when we have more number of elements, we have high accuracy, okay, but time of solving will be also high, okay. So we had to find a balance, okay, between accuracy and time, okay. As a design engineer, you have to find a balance, okay, because you cannot use too many number of nodes or elements, and then what will happen, it will take forever by the computer, okay. Forget by hands, okay, forget by hands, because if you solve a complex problem by hand using FEM, it will take a lot of time, okay. Even the computer does take a lot of time, okay. Then what we do, we find a balance, like we choose the number of nodes or elements such that we are as close to the actual result as possible, but at the same time we are using a moderate time, okay. So we have to keep a balance, okay. Now we talk about these elements, right? I told you earlier, like a cantilever beam, we can divide it into what? Discrete elements, okay. So we have different types of elements, okay, different types of elements, like line element, okay, these are the nodes, okay. And remember, in numerical methods in FEM, we always find result on what? First on nodes, okay, and then to find in between, we interpolate, okay. What we do, we interpolate. Okay, now let me prove this. If we have more number of elements, we will have more accuracy. Okay, let me give you an example here. Okay, now for example, if we have a circle, okay, if we have a circle, this is a circle, right? And analytically, what is the area of this? Area is pi times radius square, right? Or pi by 4 diameter square, right? So what will be its result? It will be 100% accurate, right? But this is what? This is analytical method, right? Because this is an equation, this is an analytical method. Now let us see how we will find the area in, for example, using FEM. Okay, what we do, as I have told you, we will divide it into what? Into, because how many points are there? This is, can you tell me, for example, let me show this line. Can you tell me how many points are there? There are infinite. Okay, infinite number of points. Okay, and can you tell me what is the degree of freedom of the whole beam? Since we have infinite number of points, we also have infinite degrees of freedom, right? But what we do in finite element method, numerical methods, we divide this. Okay, for example, this is element 1, then this is element 2, and this is element 3. Now let's count the number of points. So number of points are what? 1, 2, 3 and 4. You see, we have only 4 points now. Okay, since we have only 4 points now, 4 nodes, for example, we have finite degrees of freedom. Okay, because I will make a video lecture on degrees of freedom. Okay, but right now, for example, in in 1D or 2D, there are different degrees of freedom at nodes. So but we have right now, we have finite. Okay, they are finite. Okay, finite degrees of freedom. Okay, now anyways, since we have a finite number of nodes, we can calculate the things, the results on these finite nodes. Okay, and then we will interpolate. Okay, now let's go back to this. Now this is the circle, and analytically we found the 100% accurate area, right? Now how we do in ANSYS or abacus or the finite element method? Okay, so what we do something called discretization. Okay, we convert it into a mesh. Okay, for example, we will not go into meshing right now, but the thing is that we will divide it. Okay, that is what's known as meshing. So we will divide it. For example, I divided it into I draw 3 number of nodes, and I connected the nodes with these line elements, and we get combined, we got a 2D line element, and it is like a triangle with 3 nodes. Okay, now then we will find the area here. Okay, but remember, we didn't cover this, we didn't cover this, we didn't cover this. Okay, so this is not, maybe the the result is only 50%. Okay, so next what we do, let us increase the number of nodes. As it says, if we increase the number of nodes, the result will, accuracy will increase. Okay, so let's increase the number of nodes. Okay, this time I keep 4 number of nodes. Okay, let's connect them with line elements. Okay, so this is our area. Now you can see this one is better than this. Okay, but still it is not near 100% or 90%. It's maybe right now the accuracy is around 60%. Okay, then let us increase the number of nodes. Okay, now this time I choose more number of nodes. Okay, I choose more number of nodes. Okay, and I connect them. Okay, now this is our area. Now this is almost 90% or 95% accurate. Okay, so although this thing is still not accurate, but it is very much close to the actual value. Okay, so this is the way that I wanted to tell you. If we increase the number of nodes, okay, so in the meshing means when we divide a body, the domain, into small number of discrete elements. Okay, when we do the meshing, if we increase the number of nodes, of course our efficiency of the results will increase. But remember, we always have to find a balance between accuracy and time. Okay, so because for example, here we have only 3 nodes. Okay, we have to calculate the results only on with the help of these 3 nodes only. Then we will increase the nodes. For example, in this cantilever problem, if we have only 3 nodes, we only have to calculate displacement at these 3 nodes. Okay, then it will be less time, right? But when we increase the number of nodes, of course we have to calculate the results on more number of points, so of course it will take more time. Okay, so we have to find the balance between time and efficiency. Okay, so I think that's it for today. Okay, so see you in the next class. Thank you.